take it back to the abstract. Let me start with that. Supporting record.
Bẹ́ẹ̀ sà.
Okay. So take it back to the abstract. Take it back to the abstract. Basic abstract now.
Abstract mo wà báyìí sà. Mo ti wà báyìí.
Ṣọ́dọ̀ mi ò rà tó. Mi ò wá àwọn ègún rí o.
Ó ti wà níbi abstract.
Ṣé ẹ ti rí àbí?
Okay. So, yeah, material. So previously we have discussed what was done in this article, and what we said before was anytime you see an article like this, most especially in our own field or any other field, the very thing that you should see through is the abstract. That gives you an insight to what has been done and what is to expect in the paper. So if you look at this one here, it says in this work, we introduce two inertia type algorithms for solving variational inequality problems with a monotonicity condition that the operator is monotone and it is Lipschitz continuous in real Hilbert spaces. So the framework for the work is Hilbert space. The problem is variational inequality. The operator is monotone and Lipschitz continuous. The algorithm has inertia. So that first statement has everything that you need. The first statement there has everything that you need to know about the paper. It says they introduced two new inertia type algorithms. That's one thing. What is the algorithm meant to do? It is meant to solve variational inequality problem. And for this variational inequality problem, what type of operator? They say the operator is monotone and Lipschitz continuous. And what is the settings of the work? Hilbert space. So that is the paper in summary. Now they are trying to explain what the algorithm is. That's why the second statement comes in. They said my network went off.
No.
Okay, sir.
I want to check again. Maybe it has been sharing. You screen yẹn mọ́.
Okay, edging the share. Ṣé ẹ ti rí báyìí sà?
Good, see.
Ó dẹ̀ ti wá ṣó.
Yeah, I'm waiting. Listen. So I was saying the paper, everything that you need to, everything they've done in the paper has been explained in that first statement. And then you should be able to make your own summary out of that. The settings, the operator, the problem, and what was done. That is introduction of two new algorithms. So algorithm is inertia. Okay. So now, and I said the next statement there further explained the type of algorithm. So, and what is that? They said the first algorithm requires the computation of only one projection onto the feasible sets per iteration. So that only describes it only describes whether it is gradient projected method. That is where you can find only one projection. And another method to not to Shiruga is the same extragradient method that you should have read. Now, then she looks for the characteristic. So the first thing, and also the knowledge of the discipline is not required. The knowledge of this continuity. I'm looking at Lipschitz, but assumption requirement of that Lipschitz constant is not used. So
talking about
and then finally, also we want to fi kilo request. On fait example aussi. So tu me là d'abord.
bẹ́ẹ̀ sà.
Ben.
Okay. The network is
It's low.
So, and again, because the problem once we should be used to the problem definition now.
Yes, sir.
One describes the deviation equality problem itself. So, every other thing, these are constant to all papers. You are going to find out all those definitions and the likes. Across board. So it just seeks a point X with set plus ni kini tó wà lókè yẹn. So in C such that the inequality constraint in 1 is satisfied. So in an deviation equality problem. Now the first method not this Koplevich method method and really see these are pioneer methods. 2 to 1 our method on cutting low last visual problem here only. So but of recent our method C and we introduce, that's what I want us to go through. And algorithm 1.1. So go to algorithm 1.1. So algorithm 1.1 ye at in total 1.2. Only form basis in conservation in the article. So that we have visited that I've seen it before. So 1.1 ye. This 1.1 is a combination of what? Senk and viscosity.
Yeah.
Senk in the sense that if you look at step 2, xn plus 1 here, OJ converse combination of f of xn and zn. So what is Zn? Zn, if you go to the last line of the algorithm, they say where Zn equals Yn plus lambda n, f of xn minus f of yn. So if you see anything like that, you already know that thing has to do with Senk.
Yeah.
So that thing has to do with Senk. So which means the Senk extragradient method was combined with the viscosity technique to give them a strong convergence method for algorithm 1.1. And lambda n is computed by that update. That step size, you see, lambda n plus 1 equals minimum of that. So which means our operator F we don't need to know the Lipschitz condition of the operator, even if it is Lipschitz continuous. We don't require it. So we don't require it in the computation. So this is a Senk method which is self-adaptive and it is viscosity, which means you are going to get a strong convergence method from this. So those things, those are the key points of the algorithms. You have to know that. So go to algorithm 1.2. Algorithm 1.2 is almost the same thing as 1.1, a bit 1.2 now is inertia. 1.2 now is inertia. Same as 1.1, it is Senk, and it also has a viscosity method. and now it has the inertial step. So that's the difference. Another difference that you should note there is that the step length here is a constant. Lambda, you see lambda is not lambda n, like in 1.1. It is lambda here. So the step length here is lambda. You can see both in the seng step, that is Zn. You see that it's lambda. Then in Yn, it's also lambda. But if you go back to 1.1, we are going to see that it is lambda n. Go to 1.1. So you see lambda n. The operator, the step length controlling or scaling the operator f, it is lambda n. And we have said in 1.1 it is self-adaptive, but in 1.2, lambda, that constant, is not self-adaptive. Go back to 1.2, you see that lambda there depends on the operator because it is selected between 0 and 1 over L. So which means the lambda there depends on the Lipschitz constant of the operator. You see, lambda is selected between 0 and 1 over L. So those are the differences of those two methods. Now let's now go to the method that was introduced in the paper itself. Algorithm 3.1. So if you take some information about those other methods with you, then you are going to see what improvement has been done here. So in this main result, we have already, the first thing that we have seen there is that this method is also inertial. That's like 1 point. Yeah. It is also viscosity, like both methods.
I think.
And here, this is self-adaptive. So notably, the only improvement that this paper has done is just that it made the lambda in algorithm 1.2. It just made it self-adaptive. That's the only thing to Shimbe. That's the only improvement. If you look at 1.2 very well, and this, the only improvement that you're going to see is that what? This is now self-adaptive. And instead of it being ordinary lambda, it is lambda n, just like 1.1.
Yes, sir.
So the only improvement they did to 1.1 is that they added inertia, that's all. Because this is just the algorithm of 1.1 plus inertia. Algorithm 1.1 now plus inertia, that's the only thing that they did.
Yes, sir.
You check it very well.
Yes, sir.
And we have said if algorithms look like that, every other thing, the calculation that you're going to find in that first paper that introduced 1.1 is the same calculation you are going to find here. A bit, the only part is that inertia that these people have added to their own now. Inertia, so you have to work with inertia, then conclude it with the way those guys have concluded theirs. B1.2 should conclude paper at 1.1, take out the inertia. So those are the things that we have said before. And then we started looking at the proof itself. I think we have completed the bandedness, if I'm not mistaken.
Yes, sir.
The last time we did worked on the bandedness. So, and I want to come be we asked the reason why some of those things were estimated.
Yes, sir.
So take me back to the beginning. Take me back to the beginning of the proof. So Biba is saying, the Biba lemma 3.4. What do they want to achieve? They want to show that the sequence is banded. Lemma 3.4. Lemma 3.4. Lemma 3.4. Where are you going to?
Yes, sir. This is the.
Okay, so they want to establish the bandedness of the sequence, and that sequence also has in it variational viscosity step. So any article in this world, to low viscosity, the same conclusion. Can conclude no paper in saying, conclude the same thing. To have 15 low viscosity, to have conclude bandedness, the same way. To conclude no paper, go through every paper to low viscosity. The same conclusion on the Latifi, to have conclude kí lorúkọ yẹn, tó bá fẹ́ conclude the bandedness, it's the same thing, lemaba, across board, everywhere. So, but our steps to precede yẹn, how did they move about those ones? That's another thing entirely. But the moment there is viscosity, so they are going to conclude it the same way. Okay. Now, this first thing goes to the definition of Zn, and they said they used one lemma 2.2. So those combinations, each line, by the statement or the sentence or wherever you find the phrase, it should include every other thing that they have used to make some certain expansion and estimations. Okay, Zn minus P there, they gave the definition of Zn, which is Yn minus lambda n into Ayn minus AWN, then minus P. Then they broke that into two separate things, that they have Yn minus P, then minus lambda n into Ayn minus AWN. So that using lemma 2.2, they got this the next line there. Lemma 2.2 for the next line here. If you go to the third line, that is the first listing on the first, second on the page, onto page 213. Now, count the number of expressions. Nino equation to precede to one, the last equation can to second page here. You're going to see that you have three expressions there. Y minus B square plus lambda n square into norm of Ayn minus AWN square, then minus 2 lambda n into A inner product of Ayn minus AWN, comma Y minus P. Now, first line, page in can you expand, see how many? What you expand, see, in fact, you need 2 inner products and 3 norms.
Yes,
instead of 1 inner product and 2 norms. So what happened to it? That's where you have to figure out. Kilo tẹ̀lé mi wá láti step aláwọ̀kọ́ step ẹlẹ́ẹ̀kejì. Kilo tẹ̀lé mi débẹ̀. Now that's where you're going to now say, okay, where has the mathematics been done? Now, if you look at that, lambda n square A kìnnìkan norm àti inner product yẹn tó jẹ́ second expression and third expression yẹn, àwọn ṣì padà désàlẹ̀. So which means the work was only done on Yn minus P.
Yes, sir.
The work was done on Yn minus P. Then you now find out, okay, which work was done on it. Okay. Now Yn minus P, there is no Wn before. Now Wn has come in. So which means, okay, likely that there's an addition and subtraction of what? Wn. So those are the ways we are going to move. And just like I used to say, if you can pick a paper 2 or 3, pick a paper at least a day, even if it's going to take you 1 week to work everything they have done out, it's really going to help you. Work it out line by line, because they're not going to include every other thing there. That's why they call it research. So it's left for you to find out, okay, what was done here? Which move did they make? The moment you get used to all those things, it will be easy for you to make a translation or an extension from one space to another, from one operator to another. So easy. The more you work, the better you get at it. Okay, so we move like that. So we did that the last time, and I think we want to start. Yeah, I want to start this estimation thing. If an estimation is not clear to you, or how something moved, I need you to go through so that I can ask questions about it. Okay, what was on here? So those things, so that you'll be able to do your things by yourself. Take me to Sunsisale DSC. So these are, listen to wait here. They said recalling Yn equals PC of something like that, and by lemma 2.3. So that sometimes you're going to see using the property of metric projection. By lemma 2.3, only using the property of metric projection, because lemma 2.3, obviously what was done there is to use the property of metric projection.
Yes,
and that was what gave them that,
yes,
and equation 10 there. So then you can see they combined 9 and 10 to get what they had below. So just before we get to 12, less than or equal to here, there are only 2 expressions from which, from level if you look at the lead up to that, less than or equal to 2 and to jump 2 things. Expression make up equality. There are 5 expressions. First thing, 5. So which means they've estimated 2. And you can clearly see that second and third expression here, onako papo to for any second last line here.
Yes, sir.
So now it's left for you to find out what happened to those 2 inner products. And also equality the one better like less than or equal to. So what happened? So that you have to find out. That's a question mark. So you have to find out what happened there. So then you can continue to progress. This is common when you have a step size. 12 is always what you find there. The step size 12 is always clear. You find out that's there. So, but what they were trying to show is that the number inside that bracket is positive. They are trying to show that the number inside that bracket is positive, and that is exactly what you see in 12. So if it is positive, it means I can also estimate again to have Zn minus P squared is less than or equal to Wn minus P squared. So if both are square, we'll find out square root. That's why I got 13 to be Zn minus P is less than or equal to Wn minus P. So, and definition of Wn was used. Let's get 14 by. So definition of Wn was used to get 14. And you can see what they have said that, yeah, from the condition that goes to 0, I mean, there's going to be a positive number such that that product will be less than or equal to that positive number. So they're always with that. So that has been used again. They combine 13, 14, and 15 to give them 16. Those things you need to find them out. And this is where this thing come to 4. The viscosity method, Xn plus 1, yeah, that expansion of Xn plus 1, that's the viscosity. So the 2 articles are looking at algorithm 1.1, 1.2. If you search those algorithms and check where they worked on the Xn plus 1 minus P, you might directly, but the thing is, every article to feel a low viscosity in 17 years, any article, just name it, to feel a low viscosity. That thing you're seeing in 17, you're going to find it in the article. So that we have discussed it, take it down, the viscosity, the bandedness of the algorithm. That's it. So the next thing we're trying to establish who's about this. The problem the only that's been solved there is racial equality. And then I took you back to the relationship between equality and fixed point. We did that. That is so wrong. So which means we have the algorithm solution to climatic. So that we're going to continue again 3.5 to explain that part. So why? So that I'm going to write. So we're going to stop here, right? And continue there next week. If there's any question you ask.
No question.
Thank you very much, Doctor. The explanation was understood.
Thank you, sir. No question.
Thank you, Doctor.
Hello, sir.
Now my network went off. So since there's no question,
With question, sir.
okay, that's all we can end there. So I'm going to go through Kinito Sense so I'll get back to you.
All right, sir. Yeah, I mean, what you know, can about
the
application to be in.
Yeah, inshallah.
Thank you, sir.
No.
I will make you more.
Oh my God.